my god, that meat could have killed me.
So
bad.
Speaking of meat, I'm kind of hungry. You have anything to snack on?
Yeah, of course. You can grab anything that's in the fridge.
Audrey?
Yeah?
What is this? What is she talking
Let me go
about?
see. Oh.
Why do you have this many strawberries?
Come look at this.
What are you gonna do with all these strawberries?
Chocolate covered.
Potato chips!
Or we can make chocolate covered strawberries.
Like an experiment.
For our mass and heat class.
Let's do it.
For our chocolate-covered strawberry experiment, we will be demonstrating how heat transfer is changed due to differing surrounding temperatures. To accomplish this, we will begin by melting chocolate on a stove. The chocolate starts off in big solid clumps, but as heat is supplied to the chocolate, the molecules within the chocolate move faster. Once the melting point is reached, which is around 92 degrees Fahrenheit, the phenomenon of latent heat takes over. As you can see, once we are well above the melting temperature of chocolate, only liquid chocolate remains. Latent heat is the energy absorbed or released during phase change while the temperature remains constant. We are particularly interested in the heat of fusion of chocolate for this process, which describes the heat required for the transition from a solid to a liquid while a substance is at its melting point.
Coat 3 equally sized strawberries in one layer of melted chocolate in order to support experimental accuracy. The first bulk temperature we will be testing is that of an oven set at 200 degrees Fahrenheit. We will repeat this process of dipping strawberries and allowing them to set at different temperatures to measure the rate of heat lost in each case.
1 eternity later.
The bulk temperature of the oven did not allow the chocolate coating on the strawberry to solidify. This is due to the oven temperature being greater than the melting temperature of chocolate, thus preventing solidification from being achieved.
After taking the temperature of the chocolate again and dipping 3 strawberries in an even coat of chocolate, we placed the strawberries into 4 different bulk temperatures. These temperatures included that of the indoor temperature of 68 degrees Fahrenheit, the fridge of 46 degrees Fahrenheit, outdoor temperature of 39 degrees Fahrenheit, as well as the freezer temperature at 30 degrees Fahrenheit. We checked the coating of the strawberries once every 30 seconds to determine if the chocolate solidified by seeing if a toothpick came out clean or not. The room temperature strawberries were fully solid after 280 seconds. Those in the fridge were solid after around 287 seconds. Those outside were solid after around 137 seconds, and the strawberries in the freezer took 155 seconds to solidify. The relationship between bulk temperatures and cooling rates is governed by heat transfer principles, where a larger temperature gradient between the melted chocolate and its surroundings increases the rate of heat loss. In warmer environments like room temperature, the smaller gradient results in slower cooling and extended solidification times. This aligns with our hypothesis that the lower bulk temperatures facilitate faster solidification due to greater heat transfer rates.
To calculate the heat transfer rate, we will be using the following properties of chocolate. 44 kilojoules per kilogram for the specific heat of fusion, according to a study from J. Chevali, 92 degrees Fahrenheit for the melting temperature provided by Spinnaker chocolate, and around 1.6 kilojoules per kilogram Kelvin for the specific heat capacity, according to the engineeringtoolbox.com. We obtained the mass of chocolate by weighing the strawberries before and after dipping them and finding the difference, which was 10 grams. Using the equations for heat loss and rate of heat loss as shown here, and inputting the temperatures and times recorded during the experiment, we found that the rate of heat loss for the strawberries at room temperature was 2.619 joules per second. In the fridge, it was 3.644 joules per second. For outside, it was 5.691 joules per second, and finally for the freezer, it was 5.592 joules per second. These calculated rates align with our hypothesis to an extent in that the rate of heat loss in the fridge was greater than that at room temperature because the fridge was colder, but we predicted that the rate of heat loss in the freezer would be greater than outside, which was proven to be not true. This difference is likely due to experimental error related to the increased convective effects of the outside air like wind, which allowed the chocolate to solidify quicker outside. Additionally, in order to regularly check the state of the chocolate in the freezer, we had to continually open and close the freezer, which allowed cold air to escape and result in an actual freezer temperature lower than what was previously determined. In general, though, these results support that the solidification rate of chocolate is greater at colder temperatures relative to the melting temperature, and the rate is lower at warmer temperatures where there is a smaller difference between the chocolate temperature and the environmental temperature, meaning there is less driving force for the phase change. A chemical engineer can make improvements on this everyday process in a variety of ways. For example, our calculations prove that colder surrounding temperatures produce greater heat transfer rates while making a chocolate-covered strawberry, meaning the chocolate cools faster. Chemical engineers can then use this data to determine the most efficient method to produce chocolate-covered strawberries and other things that require a solidification phase change using lower ambient cooling temperatures, thus wasting the least amount of time and energy in the cooling process.
A few moments later.
Those were really good.
We should make more, guys. What happened to the rest of the strawberries? Wait, what strawberries?